this is Mrs. Basin, and today we're going to talk about how to do heating curve calculations. So in the last set of notes, we talked about heating curves and cooling curves. So today we're going to focus on heating curves. So what a heating curve shows us is the phase changes that something goes through as heat is added. And what we're going to focus on is we're just going to focus on the heating curves for water. So every substance has its own heating curve, but we're going to focus on water at this intro level. So when you're looking at a heating curve, if you remember, this particular heating curve, it shows the starting and the ending points of the substance. It also shows where the melting points and the boiling points are. So if you look at a heating curve, it shows the starting and ending points of that particular process for that substance. You can also tell what the melting points and boiling points are for a substance from the heating curve. So if we look at this particular one, our starting point for this one is all the way down here at minus 30. Our ending point is up here at 140. So we're looking at the starting and ending point of that graph. The melting point for this one is 0 degrees Celsius. So this is water. The boiling point is 100. So sometimes you'll see these that have temperatures on them. Sometimes you won't. If you know it's water, then you know that first flat line that you see is going to be 0. Second flat line is going to be 100. And then the problem will tell you what the starting and ending points are if the temperatures aren't given on the graph. And you'll see what I mean by that in just a second. Okay, so when you're looking at the heating cooling curve, and in this particular instance, we're looking at a heating curve, there's two different parts of the graph. You're going to see one part of the graph, like we talked about before, where the temperature is increasing. That's where you have the slanted lines. And then the other part of the graph is when the temperature is not increasing. Those are the flat lines. So when you're doing calculations for heating curves, the process that you use is going to be different depending on which part of the graph you are looking at. So if it's a point where the graph is slanted and the temperature is increasing, you're going to use Q equals MC delta T. So at that point, when you have a heating curve or a cooling curve, heat is either being added or removed constantly. So heat is still being added even when you get to these flat lines, and we'll talk about what that means in a second. But when you have these slanted lines, heat is added, the heat goes in, it increases the kinetic energy of the molecules, and that's what causes the temperature to increase. So when you're solving for the amount of energy associated with those different temperature changes, we're going to use that Q equals MC delta T that we used before. And we'll go over the specifics of the calculations in just a second. So anytime you have a slanted line, you're using Q equals MC delta T. Now, a couple things you have to be careful of when you're doing these is you have to make sure you're using the correct specific heat. So what we've done before, we've only used the specific heat for liquid water. The only time you have liquid water on this graph as in this point right here. So this would be H2O as a liquid. Below 0 degrees, you would have H2O as a solid. Above 100 degrees, you would have H2O as a gas. The specific heats are different for a solid versus a liquid versus a gas, and I'll show you those in a second. So that's one thing you have to be careful of. The other thing you have to be careful of is we're going to convert all of these to kilojoules because eventually we're going to add all of the calculations from all of the parts of the graphs together. So we want all of them to be in kilojoules before we add them up. So the other part of the graph then is those flat lines. So those flat lines happen when you have phase changes. So like I said, we're focusing on water. So for this one, we're at 0 degrees and 100 degrees. So when you're doing the calculation for those parts of the graph, it's going to be a conversion using that heat of fusion if you're looking at the solid to liquid phase change, or a conversion using heat of vaporization if you are at the liquid to gas phase or liquid to vapor phase. So that's a little different type of calculation. So the calculation that you're going to do depends on which part of the graph you're looking at. So information that you need to be able to do this is this information that we talked about a little bit before. So you might want to write this down so that you have this and you can refer to this as you're working through these calculations. So there's 1,000 joules in a kilojoule. So we'll talk about when we need that. The heat of fusion, if you remember, that's how much energy is required to change 1 mole of a substance, in this particular case, water, because these numbers are specific to water. So how much energy is required to change 1 mole of water from a solid to a liquid. Heat of vaporization is how much energy is required to change 1 mole of water from a liquid to a gas. So that's why we use heat of fusion when we're in the first phase change, heat of vaporization when we're in that second phase change. Last thing you need are your specific heats. So again, notice we said solid versus liquid versus gas have different specific heats. So liquid water, this is the one we're familiar with. So this is still joules per gram degree Celsius. If we're in ice, if we're talking about ice, then we use the specific heat for solid water. If we're talking about water vapor, we use the specific heat for water in the gaseous form. Okay, so this is how these problems are going to look. So you're going to get some information, and on the practice sheets that I gave you in your packet, it has this generic graph on there. So when you're looking at this, the first thing you're going to want to do is try to figure out which parts of the graph do you need. Okay, so some of these, like this example that we're going to do a calculation for one that goes all the way from the very bottom of the graph to the very top of the graph. So this is going to be the most difficult type. Not every single question is going to require you to do all of the parts, and we'll go through what's on your paper and your packet once we get through this overall example. So in a problem, it's going to tell you how many grams of water you're dealing with. It's going to tell you the initial temperature and the final temperature. So when you do this, you have to, like I said, first look at the graph and figure out what's your starting point and what's your ending point. Okay, so my initial temperature is minus 30. So minus 30, this is going to be ice. So that means it's going to be below that first flat line. And I can go ahead and label those flat lines to start with because these are all, like I said, these are all going to be water. So the first flat line is going to be 0. The second flat line is 100. So if my starting point is minus 30, that means it has to be below 0. It really doesn't matter where. I'm just going to put it at the very bottom here. And then steam, my final temperature is above 100. So I'm going to put that up here. So what that means is I need all the parts of the graph. And each part of this graph is a different calculation. So I can almost think of this as this is one calculation, 2, 3, 4, 5. So like I said, this is the hardest type. So this is one where it goes all the way from below the first phase change to above the final phase change. So that's going to require 5 calculations. So every section of that graph is a different calculation. Then when you get to the end of this, you're going to add all of those calculations together to get that total amount of heat that's absorbed. Now, like I said, not every single problem is going to require all 5 parts. So that's why when we get done with this example, we're going to go through that practice sheet that you have so that you have kind of a starting point for which parts of the graph that you need. Okay, so this is my overall plan here. So my substance is water, and like I said, for all the ones we're going to do, they're all going to be water at this level. We'll come back to this in AP Chemistry, and we'll do some that are not water. You have to know how much water you have, and then we have to know the starting point and the ending point. Okay, so like I said, we're going to need 5 different calculations, or this problem has 5 different steps because it's going all the way from down here all the way to the very top. So my first step is going to be a temperature change. So for that first step, I'm starting at minus 30 and I'm stopping at 0. So that's my temperature change. My second step or second calculation is a phase change from solid to liquid. My third step is another temperature change from 0 to 100. My fourth step is a phase change from liquid to vapor or liquid to gas. And then my final one is temperature change from 100 to 140. Okay, so this is my overview of what I'm going to need to do. So I'm going to have to do 5 different calculations, then I'm going to add them all up at the end. Okay, so when I do that, if we refer back to those first couple slides that we looked at, for that first step, I'm going to use Q equals MC delta T. Okay, so again, this is my first step, Q equals MC delta T, but C in this case, because I'm below 0, this is ice, so I have to use the C for ice. Phase change, using that heat of fusion. So if you remember, the heat of fusion that we looked at was 6.01 for water. Next phase, So that was 2. 3, our next part of the graph. This time it's liquid water. So this is just regular water. And then next one, I'm going to use my heat of vaporization, which was my 40.7 kilojoules per mole. And then last one, again, paying attention to the phase that this particular one is in, water vapor. So I'm going to use the C for the gas. Okay, so this is, again, my overall plan of what I have to do to solve this problem. So we're going to go through these step by step, doing these calculations. So for this first one, this is this part of the graph right here. So I'm using Q equals MC delta T. So mass is going to be 2 grams for all of these. C, because I'm talking about C for ice, I want C for solid water. So 2.06 joules per gram degree Celsius. And delta T, remember, is always T final minus T initial. So my final temperature is 0. My initial temperature is minus 30. So I'm going to take 0 minus negative 30. So my temperature change is going to be 30. So all of these should come out to be positive values because these are all endothermic processes because heat is being added in order for the substance to change phases. So these should all come out as positive numbers. Okay, so then I'm going to plug all of these in. So Q for this one is going to be 124 joules. Okay, then what I'm going to do is, since I know eventually I'm going to have to change all these to kilojoules, I'm going to go ahead and do that conversion right now. So 1 kilojoule is 1,000 joules. So that means this is 0.124 kilojoules. Okay, so that's how much energy is required for this first section of the graph. So I'm going to set that aside for now. I'm going to go to the next section. Okay, so now I'm looking at this part of the graph. So for this one, this is a phase change. So this is a conversion. So for this one, to solve for, I'm going to assume that H and Q for now, and we'll see this again in AP Chem, H, heat, and Q can be used interchangeably. So basically what we're solving for is heat. Either one of those variables for what we're doing right now, we're going to consider heat. So I'm going to say Q equals, and I'm going to start this as a conversion. So I need to know how many grams of water. So I had 2 grams of H2O. Because this is kilojoules per mole, I have to change this to moles in order to be able to use that calculation. So I'm going to use the molar mass to get rid of grams. Then I can use this 6.01 kilojoules per 1 mole. So that gives me 0.667 kilojoules. So that's how much energy is required to change 2 grams of water from a solid to a liquid. Okay, so that's my second step. Third step, I'm back to another temperature change. So I'm in a slanted part of the graph. So I'm going to use Q equals MC delta T again. Mass is still 2 grams. C, this time I'm in between 0 and 100. So this is going to be liquid water. So this is 4.18 joules per gram degree Celsius. Temperature change is final minus initial. So my temperature change for this one is 100 degrees Celsius. So again, final minus initial because I'm going in this direction. So I'm going to put those in my equation. 2 grams, 4.18 joule per gram degrees Celsius, and 100 degrees Celsius. That gives me 836 joules. I'm going to go ahead and convert to kilojoules while I'm here. So I get 0.836 kilojoules. Okay, so that's my third step. Fourth step, now I'm right here. This is another phase change. So this is my liquid to vapor phase change. So for the phase changes, for those conversions, you're going to go from grams to moles to kilojoules. Okay, so that anytime you have a phase change, that's always what you're going to do. So I'm going to start with my 2 grams of water. 1 mole of water is 18.02 grams. And then this time, since this is vaporization, I'm using the 40.7 kilojoules per 1 mole. So for this one, this gives me 4.52 kilojoules. So think about what that other number that we calculated was 0.667 kilojoules. So it takes 4.52 kilojoules to cause a transition from a liquid to a gas. So like we've talked about several times, that number, that amount of heat required is a lot greater to go from a liquid to a gas than it is to go from a solid to a liquid. Okay, so that's my fourth step. And then last one is the last temperature change. So this last little section up here, temperature change, we're using Q equals MC delta T. Okay, mass, still 2 grams. C, so this time we're above 100, so we have to use the C for gaseous water. So C is 1.87 joules per gram degrees Celsius. And then change in temperature, it's starting at 100, it's ending at 140. Final minus initial, so my temperature change is 40 degrees Celsius. So I plug that in. And I would get 150 joules. And then like we said, we're going to go ahead and change that to kilojoules. So I would get 0.150 kilojoules. So that's how much energy is associated with that last change in temperature. Okay, so now that I've done all the calculations, now I have to add them all together to get the total. Because if you remember, it asks for the total amount of heat needed to change it from that initial temperature to that final temperature. Okay, so these are all my numbers from all those calculations I did. So for the first step, it was 0.124 kilojoules. For the second step, 0.667 kilojoules. The third one, 0.836. Fourth one, 4.52, that was that second phase change. And then the last one, 0.150 kilojoules. So then I'm going to add all of those up. My total change, so all I'm doing here is I'm just adding all of these together. So my final number would be 6.30 kilojoules. So that's my total change in energy to go from minus 30 all the way to 140. So this would be your final answer. So if you notice on these, it's really important to show your work because there's lots of places where you could have miscalculations, where you can maybe not set something up right. But if you're going all the way from below 0 to above 0, then you'll need to do all 5 of these steps. Okay, so now what I want to do, if you have your packet, the next page in your packet is a couple practice problems on this. And I want to go through, if you want to stick around for a second here, I want to go through what parts of the graph you need. Because like I said, not every single problem requires you to do all 5 steps. So this is the heating curve calculations video review. It's the next page in your packet. And what we're going to do in this video that we're in right now is we're going to highlight the parts of the graph you need and talk about how many steps. And then you'll see there's another video posted if you want me to work through those calculations with you. There's another video posted where I go through each of these 4 calculations with you. If just having the graph highlighted is enough, then you can work through those on your own. Okay, so number 1 on that first problem says you have 25 grams of ice, so you'll need that when you go to start the calculations, and it's going from -10 to 150. So like I said, when you look at these, the first flat line, and again, this is because we're dealing with water, the first flat line is 0, the second one is 100. Okay, so then you can put everything else on the graph relative to that. So -10 means I'm going to be somewhere down here below 0. 150 means I'm going to end above 100. So for this first one, I'm going to need all the parts of the graph. So this first one is going to have 5 steps. This is going to be just like that calculation we just got finished with, where you do all 5 of them. So again, this is going to be Q equals MC delta T, Q equals MC delta T, Q equals MC delta T. And then this is going to be a conversion using heat of vaporization. This is going to be a conversion using heat of fusion. Okay, so very similar to the one we just did. So you're going to do all 5 of those calculations. Again, making sure that you use the right C value, whether it's a solid, a liquid, or a gas. Change them all to kilojoules, and then you're going to add them all up. Okay, so that's number 1. Number 2, I'm going to start this one the same way, where I'm going to put my 0 and my 100. This one is starting at -18, so that's going to be below 0. And then it's stopping at 25. Okay, now where it stops on this line here doesn't really matter as long as it's below 100. So I'm just going to pick a point. I'm going to say like right here. So we're going to call this 25. So that's going to be your stopping point. So that means on this one, I have 1, 2, 3 calculations. Okay, so again, first calculation is going to be a Q equals MC delta T. That's my first one. Second one is going to be a conversion using heat of fusion. Third one, Q equals MC delta T. But this time, instead of going from 0 to 100, it's only going from 0 to 25. So your temperature change is going to be a little different than what it was in that other one. So this one, you only have 3 calculations to do. Make sure everything is in kilojoules, and then you add them all up. Number 3 on that practice sheet, again, I'm going to start by putting my 0 and my 100. So this one, I have ice at 0, and it's going from a solid to a liquid. So on this one, there's no phase change. Or I'm sorry, on this one, there's no temperature change. All I need for this one is that phase change. So the only calculation I'm going to have to do for this is a conversion using that heat of fusion. So this one only has 1 step or 1 calculation. So you don't even have to add anything together on that. You do that one and then you're finished. And then the last one on this first practice sheet, again, start with my 0 and 100. This one I'm going water from 5 degrees. So I'm going to call it right here. And it's going to 95 degrees. So this one, all I need is a part of this middle section. So this is another one that's going to be only 1 step, but I'm going to use Q equals MC delta T, use the mass that's given, and then my change in temperature for this one is going to be 95 minus 5. So again, only 1 step, but when you only have 1 step and you're only in 1 section of the graph, just know that it doesn't always have to go the full length of those sections where you have slanted lines. So sometimes it might just be a part of it if you're not going all the way through it. Okay, so try these out. Like I said, if you want to see, if you want me to work through these with you, if you go to that other video that's attached to this assignment, you'll be able to see, I'll work through those with you. And in the description, it does say that the video says AP Chem because we do these in AP Chem, but these are the ones we do as review and practice. So that does go with the sheet that you have in your practice sheet. If you want to move on and try the next page, we're going to use that next page as some more practice and kind of a quiz review. So if you want to try those and continue on with those, we'll do those later this week, early next week. But for today, all you have to do is just that one practice with those 4 problems.